week we'll be talking today on some recent applications that have been published in the literature, and then on Thursday, excuse me, survey of recent topics, survey of advanced topics. So nothing in terms of lecture this week will be on the final or on the homeworks or the mini project. So there's no lecture next week. So Thursday will be the last lecture of the course. With regards to the final, it will be an electronic final. Take home, do it yourself. It's the honor code. No collaboration. You can of course refer to any course material, any Wikipedia entry, anything linked off the website, and of course clarification questions can be asked on Piazza. So it'll be released at noon on March 14th via Moodle. It'll be due 36 hours later via Moodle. It's designed to take 3 hours long, right? So this is just to give you the flexibility to choose when to take it. You can just spend all 36 hours if you want to. I would not recommend it. No.
Is it writing code or is it just
no coding? I heard a sigh of relief somewhere. So it's just so 3 hours. So it should be pretty. If you've internalized all the high-level concepts and reasoning, plus maybe some of the low-level derivations, it should be a fairly straightforward one. Like high-level concepts being things like overfitting, stuff like that. And low-level concepts being like knowing how to take a gradient. Okay, so today we will be looking at 3 recent applications, one on cancer detection using sparse models, one on learning personalization dictionaries using Twitter, and one on learning visual style using Amazon shopping data. Okay. And some of the slide material are borrowed from various colleagues. And if you're interested in the details of the papers, you can check these links out. Today, first, cancer detection. So this is based on this paper, which appeared in the Proceedings of the National Academy of Sciences in 2014. So this is the basic idea. So this particular paper was studying gastric or stomach cancer. And so suppose we had, this is a standard sort of part of the stomach, and the red part is the cancerous part. So the typical procedure in an operating room to remove the cancerous region is to have a surgeon remove some tissue, right? Then have a pathologist, which is a separate person typically, examine this tissue under a microscope. And the purpose of this is to ascertain that the surgeon removed the tissue up with a certain margin. So it's just to have a safety guarantee, right? And if the pathologist does not detect a margin, right, which means you cannot guarantee that because the pathologist only sees this part, which is the extracted part, not the unextracted part, because you can't put that under a microscope. It's not taken out of the body. So if there's no margin, then you cannot guarantee that you've taken all out of the entire cancerous tissue, and so the pathologist tells the surgeon to take some more out, and then the surgeon removes some more tissue. And this process repeats until the pathologist is satisfied, or the time limit of the surgery is of that really happens, in my understanding. Okay. So what are some drawbacks of this approach? Well, this is expensive. A pathologist is not cheap, right? Quite expensive. Slow. The examination procedure can take time because it has to be done manually. And it's often unreliable because the pathologist can't predict on the spot, in which case you might have to get a second opinion from another pathologist, which is more expensive, or you just decide to take out a little bit more tissue. I don't know the exact procedures, but those are sort of the types of options you're left with if you can't sort of make a call on the spot, right? So these are all drawbacks. So the goal of this paper was to try to automate the role of the pathologist, either to, in an ideal world, completely automate the pathologist, but that's probably not realistic in the meantime. So by having a tool that can aid the pathologist in making these decisions more reliably and faster, right? And possibly, and with less time, therefore less cost, right? So the idea is to use sparse linear models, and I'll talk about why we use sparse linear models towards the end of this first part of the lecture. Lasso, of course, originated from the statistics community, but machine learning is completely gobbled up by this point. And so here's the basic Lasso formula for regression, this should be this last one. This L should not be there for regression. And the basic idea is we want a model that is sparse, as determined by L1 randomization, that fits the training loss well, right? And so we're going to train a model to fit the cancerous regions, right? to predict the cancerous regions. Right? So it's a 3-class classification problem. There's 2 types of stomach. There's two types of stomach cells: epithelial and stromal, and then there's cancerous. And so, in order to make this prediction, the question is what is X and which is the loss function. So the X comes from mass spectrometry in this particular project, and basically how it works, high level, is you hit the sample with some ionized gas, and then you look at the spectrum of. It looks like this. There's a spectrum of measurements. I think these are sort of light spectrum measurements, right? And so different types of cells have different signatures along the spectrum. Sorry, I just don't know all the details of this spectrometry. And so the X is basically, you have a sample that the surgeon has sort of surgically removed, and it's put on sort of a plate, and then you basically discretize this 2D image. So the X is an individual cell, and there are 11,000 channels, let's say. So this is like how many pixels there are, so discretizations across in depth, length and width times depth of this, which is, let's say, 11,000. And then from that, you want to predict at each pixel where there is tissue, what is the cell type. And so here is just a visualization of X at certain, sampled at certain parts of the spectrum. So at this part of the spectrum, this is the illumination. And this part of the spectrum is illumination. So you can determine sort of very confidently what is a cancer cell, what is a tissue cell, using lab tests, but they can take up to 2 weeks, right? So that's where the training data comes from, sort of historical data of laboratory test results where you know for a fact that this tissue is cancer, this one is normal. And so at this part of the spectrum, this is the cancer cell lights up like this, and the normal cells light up like this. And red means 100%, blue means 0. And so this is just the illumination of different parts of the spectrum of cancer versus normal cells, right, for this particular sample. Okay, so that's what the X and the Y are. So that's what the X is. Okay, and so the approach that they used is multiclass logistic regression. We've all seen this already. The basic idea is you want to predict the problem. So your Y should be one of 3 classes. Sorry about that. This is binary. So the probability of each Y is log linear in a linear scoring function divided by the X within an exponent, and then you normalize by the sum over all possibilities. In binary, it's just 2. You extend to multi-class when you have K classes, and it just looks something like this. Here I'm just looking at the numerator. You divide by the sum over all possible classes to get the multi-class. So this is, you've seen this already? Okay, so what they actually use is Lasso L1 regularized, or Lasso multi-class logistic regression. So basically, the only difference is that you replace the regularization penalty with an L1 penalty instead of a squared L2 penalty. So what this gives you is a probabilistic model that, conditioned on your model parameters and an input, let's say all the spectrum readings of a single pixel, you can predict the probability of it being epithelial, stromal, or cancerous. And then the weights of this model are sparse. So very few non-zero weights. Okay. So this is the summary. So we have this real-time, we have this method of real-time imaging of tissue samples, which gives you something that looks like this for every pixel of the plate that you imaged, which is the tissue that's been surgically removed. So every pixel is an X, and each X has 11,000 features in this particular study. And this is computable in real time. That's the main benefit. And you want to make one prediction per pixel. That's sort of the simplest case. And in the training set that's used to train this model, you can get the ground truth Y via lab results, which takes around 2 weeks to obtain. So the training set contains 28 tissue samples in 14 patients, and they use cross-validates to select the best regularization strength. And the test set contains 21 tissue samples from 9 other patients. And so this is just a result from their paper, and I guess the main take-home message is that this is a fairly high agreement rate with the ground truth. So this is basically, if the model is not at least 80% confident, or excuse me, if the model doesn't have at least a 20% margin between the most likely class and the second most likely class, predicted, so they chose to interpret that as not sure, right? Because obviously you want to have some level of confidence in order to make these help in order to make assist surgeons in making these types of decisions. But overall, this is pretty good. Right? This is the confusion matrix. Any questions on the setup? Yeah.
Maybe we're gonna get into it later, but like, do you know why they chose like logistic regression? Like why?
So I think they want to be able to, so I mean, if you sort of give a model to a doctor, let's say, or someone who's not a machine learning person or a data person, they'll want to know, they want a number that they can interpret, right?
Yeah.
Most people like numbers between 0 and 1 because it corresponds to probabilities. And if you're going to make your numbers correspond to probabilities, you might as well do logistic regression, right? Because it predicts conditional probabilities. It's learning to predict conditional probabilities. Furthermore, these surgeons will not be likely to use these types of models if you can't interpret them, right? Therefore, you use L1 because L1 gives you sparse weights, right? So here is, so you know, just going back slightly. So we have for every K, for every class, so 3 classes, we have a vector of 11,000 W's, right? So here they are visualized. So blue, green is epithelial, red is cancer, and blue is stromal. And here you're just visualizing all the non-negative weights up to around 11,000, 11,500. Or sorry, this is just for just a subset of the 11,000. But you can see that these are all the ones, these are basically all the ones that are non-zero, and you can see that very few of them are non-zero. And you know, it is still a significant number of non-zero weights, but it is somehow small enough that someone who really cares about the domain can actually manually inspect all these weights. Right? It's on the order of, you know, the massive weights are on the order of dozens. Right? And one of the side effects of Lasso is that if there are many correlated features, Lasso tends to focus on one of those features, put a non-zero weight on one of those features, and zero out the rest. And so this is just showing the Lasso prediction of cancers versus stroma versus epithelial, and this is sort of the pathological diagnosis, where you want the agreement between the predicted part and the what they actually diagnose to be in agreement. Yeah.
Can we go back a slide for a second? So 2 questions here. So were they trying to have agreement in the prediction of don't know, or was that just?
No, that's just so all of these are where if your model predicts cancer, it's because the probability, because it predicts a probability distribution over 3 classes, right? So the probability of cancer is at least 0.2 higher than the probability of either epithelial or stroma. Right? And if the model predicts epithelium, so anything in this column, it's predicted because under the model, the probability of epithelium is at least 0.2 higher than the next highest class, either cancer or stroma.
Then the 90-something% agreement column, does that?
That's just this part.
Okay, so it doesn't count the don't know on either the pathology side or the algorithms.
Yeah. Although even if you do count it, I think it moves, it changes these numbers much. This is like 230, this is like 5,000 to 6,000.
So what exactly does the confusion matrix mean here?
So this is every row is a ground truth.
Okay.
Every column is the prediction made by the model. So perfect is diagonal, and all diagonals are 0.
This is not the cost that they were using in any way. It's just
these are the number of samples that are cancers,
yeah.
and of the roughly 6,000 cancer samples, the model predicted cancer in 5,809, predicted epithelial 114, predicted stroma 2.
So they didn't use any sort of asymmetric cost in.
For this particular one, no. That's certainly something that you can add to it. And so certainly that's something you can add to it. Yeah. I think if I remember the paper correctly, you can also read the paper for details. I think the training set was somehow fairly balanced, right? And so so let me back up slightly. One reason to use cost, there's two reasons to use cost. One is you have a very imbalanced data set. And the other one is you want to make sure you don't mispredict something that's very dangerous to mispredict. I think they have a fairly balanced data set, so they just thought maybe they just try to just maximize predictive accuracy, everything would be okay. Certainly this is, this system is not deployed, it's just sort of, they took an offline data set, they just said, if we were to deploy the system as is, so this is the trade-off you're making. I don't think that this is probably not good enough, I don't know, but I don't work with medical professionals, but I would imagine this is probably not good enough to be used in the surgery room, but I can easily imagine that with some more fine-tuning of the model, this can become good enough. Right? One of them may be, if it's cancers, I definitely want to predict that it's cancers. Right? I want to be conservative, which would be sort of waiting as you sort of suggested. So this, you can think of this more like a proof of concept. And the other part of the proof of concept is that this is a model that doctors can actually examine manually, exhaustively, because the number of non-zero weights is relatively small. So they can sort of really sort of know exactly what's going on in this model. Right? It's a level of verification that many machine learning algorithms cannot produce because the models are just not interpretable. So this is sort of one of those sweet spots where you have this linear model that gets pretty high accuracy, and the number of weights is pretty small, and so it checks all the right boxes where something like a medical professional or hospital might be willing to use a machine learning algorithm.
So what is this plot again here?
So it plots the weights, positive or negative, of the three classes.
So the x-axis
mass spec.
Yeah.
So this is the mass spec for a single.
No, this is the W. This is the three W's. So the W is sort of that dot product with the mass spec. The mass spec is this X, and then you dot product with the W.
These W would be the weight on that.
Yeah.
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 Sorry, so I'm still not totally sure what the horizontal axis is.
It's the weight of that spectrum.
It's so you have a.
So you have 11,000.
Yeah, I think they actually for this one. Actually, now that I'm remembering it, they may have subsampled the X's because they're kind of redundant. So here it's only about 1,000 instead of 11,000. But anyway, 1,100 instead of 11,000. Anyways, yes. So the X is a feature vector of 11,000, or if you subsample it, 1,100 values at different of intensities at different points in the spectrum of a single pixel that you image.
So
Right.
that plot on the next slide is for a single pixel.
No, this plot is the weight vector of your model. It applies to every pixel.
Okay.
It's applied to every pixel. Yeah. And the weight vector, of course, it's a three-class classification problem, so there's three sets of weight vectors, and they're color-coded. So I guess this is this is one of those cases where you sort of hit all the right checkboxes, and you can imagine deploying this in the safety critical environment because it's not only accurate but it's also simple to interpret, and therefore there's a level of trust in what the model is doing. Right. Of course, linear models are not always the best. The probability, linear models assume that the probability more or less shifts along some straight line, like normal to some hyperplane. It's often not true. And so one way to sort of instead of linear but locally linear is to cluster the X's and train a customized model for each cluster in X. Right? So just train a different Lasso logistic regression model on each cluster in X. And so long as the number of clusters X is not too large, this is still roughly speaking interpretable. And this is just a different experiment where they looked at the error metric, and then you get a slight reduction in error if you use this customized training. Okay, so just to recap, this seems really awesome. Why aren't we deploying this right now? Any ideas why? okay, we tested this on 9 patients, right? 9 patients does not a conclusive statistical proof make, right? So in order for this to, I think, really be widely adopted, you need to test this on, I don't know, 1,000, 5,000 patients. I don't know what the number, I don't know what the standard is at the NIH, but you know, something much larger than 9. Okay. It's promising, right? This is certainly promising enough to, because keep in mind that you trained on 14 patients that were not these 9 patients, right? So it was, it's completely out of sample testing in some sense, but it's still only 9. And you know, this is also sensitive to this specific imaging technique. If you get a new imaging device, this whole process needs to be retrained, right? So there's a number of issues that you need to deal with before this becomes sort of a viable, standard, systematic, robust, verified process that a hospital would use. Right? And of course, machine learning is only part of the solution. This does require infrastructure and investment, and not everyone has a spectrometry device for every surgical room, right? And you know, when I say that you can analyze the weights to sort of make sure that what the model is learning is scientifically legitimate, this does still take time, right? So you know, one common thing that people do in these sort of scientific analysis of computational biology type domains is that they train a model, let's say it's sparse. For every weight, you have to like point to a paper publication that sort of studied this particular weight and it's confirmed that everything sort of lines up, right? That can take time. Not an astronomical amount of time because the number of weights is, you know, pretty small, but you can easily imagine that this could take 2 years, right? Or more. Obviously, there are sort of political, legal, social issues, right? There's a misprediction who's at fault. We're already dealing with this with the Google self-driving cars. If there's a crash, who's at fault? Same issue, same type of issues come up here. Okay, so this is probably the simplest of the 3 applications I'll be talking about today. Any questions on this before I move on?
Yeah, exactly on this, but do you know of any machine learning deployed products in the medical field, in the radiology or anything?
Deployed. I am unaware of one that's, I'm sure, I'm almost sure that there is something deployed, I'm just not aware of it. There are lots of these sort of proof of concept studies that have been done, have been published in various medical journals. And they all seem very promising, say, for various practical issues of deployment. And in fact, I mean, they all suffer sort of the same issues. In terms of actual deployment, yeah, I'm not aware of one. Yeah, but I would be very surprised if there wasn't something. Okay, so the next topic is on learning dictionaries for personalization via Twitter data. So this is based off of this paper representing documents through their readers, published 3 years ago now. So the motivation for this paper, so this is something, okay, by the way, time for something completely different. So the motivation for this paper is that, you know, many sort of media outlets and news channels are producing increasing amounts of news articles on the internet today, and so in the sense we're overloaded by news. In fact, there are over 1 million news articles or blog posts generated every hour now. Kind of insane to think about. And so, you know, the way to deal with this, one way to deal with this is to have personalized recommender systems that recommend sort of a small set of news articles in this particular case that any particular user might find interesting rather than having to browse through, you know, a sea of uninteresting news articles to this person. So let's say we have a corpus of news articles with some sort of representation. That's this vertical bar. And this representation can be, you know, bag of words, outdated topics, word to vec, even. And then we have this user with some preferences, unknown to the recommender system initially. And so one way to sort of learn about the preferences of this user is to, you know, look at historically what the users have recommended, and let's say what users liked or retweeted, or, you know, some type of positive interaction that's been logged by the system, right? And let's suppose in this particular case, for these 3 recommended news articles, the user liked or retweeted or had some positive interaction with these 2 articles. And so that can be saved as a way of sort of measuring what, what types of articles this particular user finds interesting, right? So you can learn to personalize the users from their historical data. The challenge in this regime is that many common representations don't naturally line up with user interests, right? So fine-grained representations such as bag of words are too specific, right? So if you do a word bubble of all the words in this article, you get something that looks like this, right? It's a little bit too fine-grained. High-level topics, such as from a topic model, too fuzzy or too vague, and it can also be inconsistent over time. Right? So we really want something that's sort of in between these two in terms of the level of granularity. And so the goal is to improve performance through a more natural, improve recommendation performance through a more natural document representation. And the opportunity is through social. So most people these days find their news through social networks rather than through, let's say, Google search or even the homepage of a news of an online newspaper like this is the New York Times. And so there's lots of social interactions. You can, on this New York Times article, you can share it by Facebook, tweet it via Twitter, share it on Google+, so on and so forth, right? So we're going to look at Twitter for this particular project. And here's a Twitter profile, right? And this, here's a tweet of an article, right? So this Twitter user is called Substandard Nerd. I think it's a real Twitter user. And this person tweeted this article, right? And we're going to think of this tweet for now, for simplicity, as a positive interaction. The reason why this user tweeted this article is because this user somehow identifies with this article, wants to share this article, would have liked to read this article, been recommended this article by the system. Let's look at the profile of Substandard Nerd. So the thing that we're going to focus on in this part is the fact that I don't know about most, but many Twitter users use what we're going to call badges, which is basically a list of sort of almost like tags that this Twitter user identifies with, like gig going, festival attending, music loving, Linux fettling, Perl hacking, cycling beat. Okay, I'm starting to think this is not a real Twitter. I borrowed these slides from one of my colleagues. Okay, so this is sort of the motivation, right? We have these people. They identify with these sort of badges, and then they also identify with these news articles, right? And so can we learn a representation of our documents based on how users share them, right? Based on how users identify with them. Right. So for example, can we learn from millions of sort of tweets of this form and millions of profiles that the reason why this Twitter user tweeted this article is because this article belongs to the music badge which this Twitter user identifies with. So you can think of this as sort of the concepts. This is the actual article. So this is what we have. We have the Twitter user, we have the user IDs with a set of badges that the user identifies with. We have a set of tweets that every user gave to an article, and then for every article that has been tweeted, we have the words of that article. Right? So using many tweets, can we learn that someone who identifies with the badge music in their profile, which is in their profile, reads articles with these words? Right? That's the idea. So in this particular project, they were given a training set of tweeted news articles from a specific period of time. This is 3 million articles in total. So step 1 is to learn a badge dictionary from the training set. So here, basically, recall that badges are the tags that a user identifies with in their profile. So for every unique badge, so we collect the union of all badges from all the Twitter users in this training set. We want to learn a word representation of that badge. This is what they call a badge dictionary. Right? So for example, if this is all possible, if this is all the words, the entire vocabulary, this is all possible badges. So words might be in the millions or even billions in the case of Twitter because of all the abbreviations people use, and badges might be in the range of, I forget exactly, probably in the range of 100,000 maybe. then every badge gives you something looks like this. So this is just a word cloud representation of this column. So large just basically means this badge uses this word more often, and small means this badge uses this word less often. Okay, so given these badges, we can use badges to encode articles, right? So if you use badges to encode articles rather than words, right? So you could think of this as you could think of this as dimensionality reduction in the lingo of the things that we've looked at in class. It's just that this particular form of dimensionality reduction is based on social sharing rather than something completely unsupervised. Right? So this is sort of, you can think of this as sort of a more supervised version of dimensionality reduction. So, based on, if we represent this as a linear combination of badges, this article as a linear combination of badges, then if we visualize those badges, then we can get something that's a little bit much more cleaner than, let's see, than something like this, right? So that's the basic idea.
There's a badge called divorce.
I'm sorry?
Someone has a divorced badge on this social account? Okay. What is that?
Well, it could.
So divorce people like this art?
Divorce and then exactly.
No. This is the word representation of a mixture of badges. So this is doing dimensionality reduction, right? So it says I'm going to represent articles as a linear combination of badges, right? And so there may be words that belong to this article. So normally when you visualize the most common words of this article is just look at the frequency of words. But now we're going to represent this not as words, but as a linear combination of badges. And then we're just going to visualize the most common words in that linear combination of badges. This will include words, so this is just words. This will include words that don't even appear in this article, because there are other articles that are also represented by a similar linear combination.
Those are all badges.
These are all words. So this article is represented as a linear combination of columns, right, of badges.
Yeah. Okay.
And it'll become clear in a couple of slides, maybe.
But those are not badges.
These are not badges. No.
Oh, okay. So
These are words.
weird badges, yeah.
Yeah, these are words. Basically, the point is that for high-level representations like topic models, you might learn there's 20 topics in a Twitter in a news. There might be 20 topics in the articles tweeted about on Twitter. That's too coarse grained. There's millions of words. That's too fine grained. There are maybe 100,000 badges, let's say. We want to reduce the representation from a vocabulary over millions of words to, let's say, 100,000 or 50,000, however many badges there are. So that's the dimensionality reduction step. You can nonetheless visualize badges or combinations of badges using words, because every badge is associated with a set of words. And so this is the visualization of the linear combination of badges used to encode this article. This will become clear in a few slides. So the advantage of badges is that if you look at an individual badge, you can sort of quickly get a sense of what are the sort of the important words that are associated with this badge. So it's interpretable, and each dimension, since this is dimensionality reduction, we're reducing from, let's say, 1 million to 50 or 100,000 dimensions.